Alright, so if you guys want to turn to 5.4 day 1. Alright, Joshua, we already discussed what you're going to do. Okay, so like I said, it's actually going to be very much a similar thing to what we've been doing. So to start off, the fundamental theorem of calculus part 2, I'm going to actually write it up top in that space right there. So the integral from a to b of f of x is equal to big F of b minus big F of a. Yes, there is a dx. Missed that. Alright, so I'm just going back through the same exact steps that you've done before. Find f of x, which is the antiderivative. And remember, no plus c for now, because we're doing a definite integral. Step 2, evaluate f of b and f of a. And then I'm going to rewrite here, f of x evaluated at b to a is equal to f of b minus f of a. So everything you've seen before, and I'm forcing you guys to see this notation over and over again just because I don't use it that often, but I don't want you to forget what it looks like. Okay? So the example 1, I always start with this example on this day because tomorrow you have your 5.1 to 5.3 quiz. And something like this could be on tomorrow's quiz. So you want to think about, well, how do you find the antiderivative? So what I want you to look at is, let's pretend that it wasn't an antiderivative. Let's pretend you were taking a derivative. What rule would you need to take the derivative? Product rule. So if you need a rule to take a derivative, it means you probably need a rule to take the antiderivative. We don't know any. So here's what you're going to do. Every problem you look at, you're going to say to yourself, is there a rule? And if your answer is yes, product, chain, or quotient, you're going to say, then you can't do the antiderivative, so simplify. You have to simplify because the only rule that you can do right now is power. You can only reverse a power rule right now. Okay? So if there's a product, you're going to multiply it out. If there's a quotient, you're going to separate terms and don't do a common denominator. You're going to do separate denominators. Okay? You want to make sure. If there's a chain rule because something is to the third power, then you're going to have to multiply it out 3 times to get rid of the extra rule. Okay? So we're going to simplify it. We're going to change the problem so it doesn't have a product rule in it. And you want to remember that for tomorrow. You can't do any rules yet. Only power. So I'm going to multiply it out and we get 2t squared minus 3t minus 2. So I skipped a little step. I didn't do the 2 terms. And then just using the fundamental theorem of calculus part 2 says that's how you do your actual definite integrals, the same exact way I taught you before. Now it just has a name, FTC2. Alright, so find your antiderivative. After you find your antiderivative, we're going to find f of 4. After that, we're going to find f of 1. Alright? So let's do our antiderivative, make sure we remember how to do those rules. So I'm going to add 1 to that power, so I definitely get t cubed. What's the coefficient in front? 2/3. Yep, 2 over 3. T cubed. What's the coefficient in front of the next term? Negative 3/2. Good. T. Last term? Oh, it should be. Thank you. Last term? 2 squared over 2. No. You mean for this, Danny, or last one? The last one, it doesn't have a t, so I'm going to add 1 power and then divide by the 1 so that it cancels the 1 on the bottom. Okay? For this one, I'm going to let you, honestly, no, this would be a non-calculator question, but just to save a little time, I would like you to evaluate this using your calculator. And when I say evaluate, not f and int, I want you to actually find me f of 4 and actually find me f of 1 very quickly. I would get your calculators out because I am going to mention how I think would be the best way to do it. So the best way to do this is right now put the antiderivative into y1. Put the antiderivative in y1. So press y equals y1, put that in. Because now you're going to come to the home screen and you're going to do y1 of 4 and then you're going to do y1 of 1. And it will be much faster than the rest of you who are probably trying to substitute in 4 on your blank screen and then redo the whole thing with 1. Ramsey, if you could make sure Hikaru followed those steps. You know what you're doing? No? Help her out. Thank you. Alright, so f of 4. I want a fraction, please. I want a fraction, please. I want a fraction, please. 32 thirds. I hear 32 thirds as an answer. Can I get confirmation? Okay. Anthony, you know your calculator will turn it into a fraction, right? Okay, I just wanted to make sure. I don't know what you're talking about. If you press enter and you have the decimal, press math, enter, enter. Put 0.5, enter. 0.5, enter, and then press math, enter, enter. Yeah. Oh, yeah, so I got you. Do you know why I don't like that method? Do you remember the reason? It only works in the window that you have. So if any of the values are outside of your window, your calculator is going to say error. Okay, just saying that. I'm not repeating. Someone help him out. All right, f of 1. Negative 17 over 6. All right. So to find the actual answer, I would do 32 thirds minus negative 17/6. Don't forget to minus a negative. You'll even see me make that mistake here and there. Minus the negative. All right. And what do we actually get as our final answer? 264 plus 70, 80. Oh, really? 81 over 6? 27 over 2? I believe. Okay. Sometimes my math works, sometimes it doesn't. All right, major thing I want you to get out of this, nothing is new. I wanted to remind you, if you're going to use a product or a quotient or a chain rule to do the derivative of the problem, meaning let's pretend it's not an integral problem, then you know simplify. You have to simplify it so it's separate terms, okay? Let's look at the second one, which is a little bit harder. It has the integral of cosecant of 2x times cotangent of 2x. So this one definitely has rules everywhere. It's got a product rule, it's got a chain rule if you wanted to do a derivative. This would be hard to simplify. You really would have a hard time simplifying it. So what we're going to do instead is think about there must be a rule that we know. What is the rule that gets us a derivative cosecant of something, cotangent of something? Whose derivative is that? Cosecant. So the cosecant of u's derivative is, it's a co-function, negative cosecant u, cotangent u, multiplied by. Alright, so let's restate what happens. Your inside stays the same, and you're multiplying by the derivative of that inside. Alright, so now we're going to try to do this backwards. You're just going to use logic to figure it out. Later, we're going to learn a method to actually get the antiderivative. We're just going to use logic. So, we figured out to start that we're going to be using some form of cosecant of, and the inside, what happens to the inside each time? Stays the same. So the 2x better still be there. If I took cosecant of 2x's derivative, would it be positive? Cosecant of 2x's derivative, cosecant of u, would it be positive? No. So what should I add in? A negative. Alright, so we got a negative. Divide by 2 2, you want to say, not the x. Because remember, we only multiply by the derivative of it. So then we divide by the derivative of it. So divided by 2 is the same as multiplied by a half. Joshua, you can take the seat right there. It's a little bit closer. And then we're going to double check it. Because we want to make sure that if we do this, that we did it right. So I'm going to take the problem that's there, the antiderivative, I'm going to take its derivative. So when there's a coefficient in front, what do I do with the coefficient? We drop it down. And then the rule for cosecant of 2x would be negative cosecant of cotangent of, but leave the inside exactly the same, multiplied by the derivative of the inside, which is 2. So let's double check. Does this work? This 2 gets canceled by this 2, so that worked. This negative gets canceled by this negative, so yes. I ended back up with the original problem, so I know it's correct. Okay? You have to know your derivatives really well to be able to do your antiderivatives. Makes sense, right? We're just going backwards, so you do need to know your derivative rules very well. Alright, so we got our antiderivative, and now we're going to find f of 5 pi over 6. The negative came from the fact that the derivative of this gives me a negative cosecant, so I need to use a negative to not have it there. And then the divided by 2 comes from multiplying by du dx. You would multiply by a 2, so now I'm going to divide by the 2 to do the opposite. Does that make sense? And then you double check that you did it right, because the first few of the harder ones you do, you're going to probably get a few wrong. You want to double check your derivatives. Alright, so I'm going to evaluate those two. I'm going to get this out of the way. Alright, so if I want to evaluate these, let's actually write down what I'm going to evaluate. I would have negative 1/2 cosecant of 2 times 5 pi over 6. So I get that. Negative 1/2 cosecant of 2 times pi over 6. And I get that. Alright, so what do we get? Negative 1/2 cosecant of 5 pi over 3. I'm going to do this a little different than the other class. Negative cosecant of pi over 3. So that's where we're at. Cosecant is the reciprocal of what function? So I'm going to say it one more time. Cosecant is the reciprocal of what function? You guys can yell it out.
Sine.
Alright, so why is there only 2 people that I'm hearing? 3. Yeah, they say it louder. Alright, I'll take that as the reason. Okay, so before I even try to evaluate, you should always be taking any trig question you have. So this part of the problem, you draw your axes, figure out what quadrant you're in. 5 pi over 3 is in which quadrant? 1, 2, 3, or 4? Okay, where you are. You have to know how to do this.
4.
Someone give me a good reason why it's down there. Because it's almost 2 pi. That's a very good reason. 6 pi over 3 would be here. It's 1 pi over 3 before that. That's why it's in the 4th quadrant. Cosecant is the reciprocal of sine. So is the cosecant here positive or is it negative? It's the reciprocal of sine. So is the cosecant positive or negative in the 4th? It's negative. It has the same sine pattern as the sine function. Alright. This one, first quadrant, much easier. First quadrant, sine is positive in the first or negative in the first? Positive. You don't want to forget this because most of the times the mistake you make is if it's negative, you forget your negative. That tends to be the mistake. And then obviously the second mistake is not knowing your values. That would be a huge no-no. Huge, huge no-no. I'm going to run out of space. Let's make this smaller. There we go. Alright, so we get negative 1/2 multiplied by the cosecant of 5 pi over 3. So what is the sine of 5 pi over 3? Negative is correct. Negative square root of 3 over 2. Let me double check that. Okay. So it would be negative 2 over square root of 3. Simplifies to 1 over square root of 3. Nice thing about AP Calc, you don't have to rationalize your denominators unless it's multiple choice and their answers are rationalized. When you get an answer and your answer doesn't look like their answer, then you have to simplify yours fully. If this was free response and you wrote that answer, it would be accepted. Okay? Second part, we get negative 1/2 multiplied by the sine of pi over 6 would be positive root 3 over 2. Therefore, I flip 2 over root 3. And we get negative 1 over root 3. And so the final answer for this guy would be 1 over root 3 minus negative 1 over root 3. And we get 2 over root 3. So you do have to be able to just go backwards with a derivative for now. Okay? 2 over root 3 is the exact value. That's what it's called. I don't know. Alright, fundamental theorem part 2. Take another look. This is, again, something you've done already. Okay? I'm going to write down what it is and then try to explain where you've already seen it. So let's look at the integral from a to b of f of x dx, I keep forgetting that, is f of b minus f of a, what we just did. But I'm going to take this f of a and add it to the other side of the equation. So it's on one side of the equation. I get to move it to the other side. It was a minus, so I'm going to add it. So what do we end up with? We get this by itself. I'm going to actually write that in front. This was all the way in front, added to the integral from a to b of little f of x dx. So where have you seen this? To get an ending value, you need a starting value plus the displacement. So let's look at example underneath. At time equal to 1, so first thing I do, any type of word problem I get, I turn everything into notation. At time equal to 1, the particle's position is 2. At time equal to 1, the position is 2. You don't rewrite it with words, you use all the notation. Given v of t, which is here, is 2t squared minus 1, find the position of the particle at time equal to 4. I want to know the position of the particle at time equal to 4. And we already talked about this. If I want to know the position at time equal to 4, let's start with, if I have velocity, what do I need to do to get to position? Antiderivative. And we have 2 times. I need someone to tell me in words, what does just this part of the integral give me? Just the integral from 1 to 4 of v of t. Whoa! This thing moves. Annie, what do you think? The net signed area is always what an integral gets me. Perfect. Now I want you to kind of put it into terms of the question, which is particle stuff. So who's net signed area? So net signed area, true, but now we're talking about velocity, we're talking about position, we could talk about acceleration. I want it in terms of that. So your answer is 100% correct. Can someone elaborate and put it in terms of this problem? Yes, Danny. It's velocity's net signed area, which means what? Got to keep going. Anthony? So we just went from net signed area that I said was correct to total area. Are they the same thing? No. So we're not going to go to total area. We're going to stay with net signed area. We're going to take Danny's answer, which was the net signed area of velocity. But I need more. And I know, Joshua, you have the answer. I'm trying to see if I can get a few more people that are usually a little bit more quiet. All right? You want to try again, Anthony? And then I'll go to Noah. What just from 1 to 4? So everything you said was true. The net signed area of the velocity from 1 to 4. That word area, does that make any sense with velocity in the real world? No. So obviously it makes sense in calculus, but I need it to make sense in the real world. This is a real world problem. We wouldn't be talking about area. So you have to understand what that means. By the way, that's on the test tomorrow, meaning you've already learned this. Don't use total, because we already talked about we can't use total area. The distance moved by the particle along the interval from 1 to 4. What kind of distance? So explain to me, if I'm standing here and I run around the school and I come back here again, is my distance going to be however many feet I ran, or is the distance you're talking about 0? So your answer would be, for my example, 0? Yes. I will take your answer. Can someone take his answer and use maybe a better word to describe exactly what he just said? Noah. Thank you. Thank you. We went through all of that to go back to exactly what is sitting in your notes from, I don't even know when, but just sitting there in your notes. The integral of velocity gives you the displacement. That's it. You could have just told me that. We would have been done with this a while ago. Oh, man. Should have raised your hand, Lafika. All right. All right, so we get the displacement. And what did we say about displacement? If I want to know where a particle or where someone ends up, does the displacement give you that answer? No. What do you need to know? Where it started. We started this problem at time equal to 1. It started its position at 2 and then gained a displacement of whatever this value is. If the value is negative, it means I ended up back behind where I started. If it's positive, I ended up forward from where I started. Therefore, to solve the problem, let's come over here. Let's do the antiderivative of the velocity, which would be 2/3 t cubed minus t. We're going to be finding the antiderivative at 4. And we're going to be finding the antiderivative at 1. Try to remember what these values were. All right, so let's see. Was that correct? Yeah. All right, 64, 128 minus 128 minus 12, 8 is 16. Wait. Yeah, okay. And then 1 would be negative 1/3. Therefore, my value would be 1/16 plus 1/3, which gives me a total of 117 over 3. But 117 is divisible by 3. How do I know that? Not because I'm a math genius, but because 1 plus 1 plus 7 makes 9. 9 is divisible by 3. Therefore, 117 is divisible by 3. And what is 117 divided by 3? 39. Perfect. So, what did we figure out from this problem and the integral? We figured out that the particle started at a position of 2 and then gained 39 feet, miles, whatever unit this is going in. So the answer to the question then becomes, we're now at 41. Okay? You have to remember how to figure out what the integral means. It's huge. It is very, very important. So how do I know what the integral means? When I take the integral of something like velocity, I would get position. So what does the integral get me? It gets me the net signed position, or the net signed distance. If I take the integral of, say, gallons per mile, I know I'm going to end up with the net signed gallons. And the other word you can use for net signed gallon, the change in. All it finds for you is the change in. So a plain old integral gets me the change in, whatever the units end up being. Because I've taught you how to find the units of an integral. Take your integral, figure out what the units are, and let's say the units are miles per hour. You found the change in miles per hour. So if the answer is 20, then you went 20 miles per hour faster than before. If your change, so your integral, the units end up being gallons, and your value for the integral is negative 20, then you lost 20 gallons. Okay, so it ends up that the plain integral is just the change in the final units you get. Not the units of this. So it's not the change in velocity, it's the change of the integral of velocity. So the change in position. Okay? Does that explain kind of integral a little bit better? Oh, so like f of x? So if I found like the antiderivative of little f of x? The reason I don't say that is because you're going to get things like blood pressure divided by the diameter of a vein and one derivative back. You don't know what that means because it's not a problem you're used to, but they're always going to give you units, and you'll be able to multiply your units to be able to go back one. That's why that unit analysis is so important, because you will get things like an amusement park, and suddenly you're looking at cost per person, and then the integral going back will probably get a cost, so it'll be the change in cost. So no matter whether you understand what the problem is talking about, you'll always be able to analyze the units, and then knowing the definition of integral being a change in, you'll be able to figure anything out. That's what I really want you guys to get. Anthony, what's up? Yawning? Boredom? My class is just that boring? Thanks. Anthony now thinks my class is really boring. All right, yes. At time t, the velocity is 5, like a physical number, you mean? And then they'll say the position at that time is, in general, is... Okay. They don't need to. You don't need the extra point. When you take a derivative, it gives you exactly what it says. You don't need extra information. It's the antiderivative that you need extra information. So what I mean by that is if they give me position and I want to find the velocity at 5, I'm just going to take the derivative and put in 5. But if I have the velocity and I want to find the position at 5, then now I need to not only take the antiderivative, but I also need a starting position. So, like I said, the antiderivative is trickier because you need more information to answer essentially the same question that you used to do with a derivative. Does that answer your question? Okay, cool. All right, so stop this guy.